Hello, my shimmering stars. Today, I, Shaurya Grover, welcome you all to this amazing platform of PW English. Yes, my dear students, today we are going to start with lecture number 2 based on the chapter DNF block elements under our batch Excellence batch. I hope so, students, you have seen the previous lecture and all the topics were clear to you. Today, we are going to proceed towards the next topic with regard to the D block elements. As you have seen in the previous session that we have done the general introduction with regard to D block element and F block element, and we got to know about the electronic configuration, we got to learn about the tricks, how to learn the elements. Yes, so in this particular session today, we are going to proceed to D block element, and after that we are going to complete the F block element. So this is going to be our order. Now if I talk about D block element particularly, we are going to focus upon the properties of D block element in this particular session today. As you all know, our batch name itself is Excellence batch. So yes, we have to do a lot of hard work in order to excel in our field. This I say in each and every lecture of mine. Yes, I hope so you are working really very hard, and trust me, my dear students, this process of working day in and day out will give you a very tasty fruit in future. Okay, so just keep going and don't feel demotivated. Just make yourself confident, have faith in yourself, and just keep going on, right? So now let us start our today's session. As you all know that we are going to do the properties of D block elements. So our today's topic is going to be the properties of D block elements. Now students, before moving on to the D block elements properties, I am showing you a periodic table over here again that we have seen in the previous lecture as well. So my question, I shall be asking you some of the questions with regard to the previous lecture. So it will be a kind of a revision also, and then we will move further. So basically students, if you remember, I told you about group number 10. Group number 10 was used for the hydrogenation process in organic chemistry during certain reactions. Nickel, platinum, palladium, they were used as a catalyst. This I have told you in the previous lecture. Yes. If I talk about group number 11, they are used for as a coinage metals. Do you remember? Great. If I talk about group number 12, which is really very important because you are going to see in most of the physical properties, in most of the properties with regard to the D block elements, group 12 will show a different scenario with respect to the other elements. So group number 12, they are referred to as pseudo transition elements. If you remember in the previous lecture, I told you what is the difference between transition elements and what is the difference between pseudo transition elements. Now let us give a quick recap to that. D block elements are referred to as transition elements, except group number 12. Why? Because group number 12 are pseudo transition. What is pseudo word? Pseudo means fake. If I say pseudo happiness, that means it is a fake happiness. If I say pseudo smile, that means it is a fake smile. Similarly, if I talk about pseudo transition elements, that means they appear to be transition elements because they actually come under the category of D block elements, but though they are not transition elements, they are pseudo transition. They appear to be, but they are not. For example, if someone is smiling in front of you, it is not necessary that the person is inside out happy. So that means if someone is faking a smile in front of you, that is a pseudo smile that they are giving you, but in actual they are not happy. So that correlates over here. I guess now the pseudo word is quite easy for you to correlate, right? So I have told you why they refer to you as pseudo transition elements, why they are assumed to be transition elements but are not. Because they exhibit the property of D block elements. Now what is the property of D block element? That the last electron shall enter into D subshell. Yes, that's why they refer to as D block element. But again I'm saying, because over here they have completely filled D subshell configuration, that's why they're pseudo transition. While in the case of I'll talk about transition elements, that means I'm talking with regard to group number 3rd and group 2, group number 11th. These elements are transition elements. All from group 3 to 12 are D block elements. No doubt they are D block elements. From group number 3rd to group number 11 are transition ones. Why? Because they have incompletely filled D subshell. That means there shall be electrons which can show transition from one state to the another state. But the group number 12 cannot do that. Why they cannot do that? Because over there is a completely filled electronic configuration in the D subshell. Great. So now you are aware of the two terms, transition as well as pseudo transition. Now if you remember in the previous segment, I've told you What were F block elements? They were inner transition elements. Okay, what were S block and P block elements? They were representative or the main block elements. Yes, so that was a quick review about it. Now further, adding on to this periodic table, I have already told you that from here you can see in group number third, when you have seen there is lanthanum after lanthanum, from 58th element to 671 element we have lanthanoid series. That means the F block element arises over there. And from atomic number 90 to atomic number 103, again we have F block elements that are referred to as actinoid series. So basically these two series are aligned over here below, they are F block elements. Great. Okay, now students, moving on to our very first very first property over today is atomic radii. If you remember in the previous lecture, when I was explaining you with regard to the properties of the D block element, I have already told you that D block elements are the transition metals. Basically they are metals. They will show the properties such as malleable, they are ductile, they have high tensile strength. Okay, and other than them they are lustrous. We have seen these properties in the previous segment, but today we are going to start with the most important property with regard to the D block element, that is atomic radii. It is very very important, so kindly listen to me very carefully. Now when I am talking about atomic radii, I am moving from left side to right side in a period. This is my first concept. Second is, either I will be going from top to bottom in a group. So I shall be considering period as well as group. First of all, we shall be considering the period. Okay, in a period, what is going to happen in a period? Kindly observe very carefully, students. This is really very 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 important. You have to put a huge star mark on the topic atomic radii. Now if I talk in a period refers to as from left direction towards the right direction. Now let us see in the periodic table, making more clear to you, from left to right, from left to right, from left to right. I'm standing over here like this. This is my right side, this is left side. So from left to right, from left to right, from left to right. Yes, okay. So when I'm moving from left to right, we all are aware that in a periodic table, basically the size will decrease, but this doesn't happen in the case of D block elements. There is an exception over here. What is an exception, ma'am, over here? For that, we need to write the elements in the D block series. Now, first of all, I'm going to write the 3D series. What was the 3D series? 3D series basically is referred to as period number 4. If you remember, I have told you in the previous class about this topic as well. That this is your 3D series. 3D series is group number is period number 4. This is your 4D series. That is your period number 5. This is your 5D series. This is your 6D series. Do you remember this thing? Now, I am going to write the 3D series first of all. I am going to write over here the 3D series. The 3D series. What were the elements that were present in 3D series? I have given you a short trick to remember them. And I've already told many students that if you have a certain trick that is quite easy with respect to the trick that I have given, kindly write in the comment section, which I have seen some of the students have done so. So it is up to you. Whosoever you feel it's easy to remember, you can do so, you can learn it out. Now, what trick I have given was school teacher values chemistry mechanism. Now over here, chemistry mechanism, either it can be a reaction mechanism in organic chemistry or whatsoever the problems you face in chemistry. Okay, so basically what is the trick? School teacher values chemistry mechanism which brings faith, confidence and comfort zone. This was my trick for 3D series. If you remember, this was my trick for 3D series. Now according to this trick, I am again writing. If you have not seen the previous lecture, there is no issue, students. Over here I am writing it again. You can write along with me, right? So first of all, I am saying school teacher. School refers to as scandium. Teacher, titanium. Values, vanadium. Chemistry, chromium. Mechanism, manganese. Which brings faith, iron. Okay, faith, confidence, cobalt and nickel. Okay, and then was comfort, that is Cu, copper. Zone, that is zinc. I am writing the short trick over here. If you have not written in the previous lecture, you can write. It is school teacher values chemistry mechanism. Now I have added two major words over here which are not included for elements, that is which brings faith, confidence and refers to as ND over here. Okay, I'm taking and. Okay, and comfort zone. Okay, so this was my short trick which I have given you in the previous lecture. Now students, you can, if you want to write the name of these particular elements, you can also mention them. This is scandium, it's titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Is it clear to you? Okay. Now students, moving on, if I have to tell you about the atomic radii, see what happens when you move from scandium towards magnesium, sorry, towards manganese, not magnesium, towards manganese. When you are moving from scandium towards manganese, from left direction towards right direction, over here atomic radii, over here atomic radii or atomic radius, you can say, it decreases. Now I shall be using decrease symbol as like this. Again and again, I'm not going to write the decrease word. Okay. So atomic radii decreases while you are moving from scandium towards manganese. After that, from iron, cobalt and nickel, the atomic radii remains same. The atomic radii remains same when we talk about iron, cobalt and nickel. And at last, when you move from copper towards zinc, atomic radii increases. Now usually what happens, usually atomic radii will decrease when you move from left to right direction, but over here in 3D series, in 4D and 5D, what we have observed in D block elements, basically first of all the atomic radii will decrease, then the atomic radii will become same, and after that the atomic radii will increase. Now what is the responsible phenomena that this change we are observing in the D block elements? So for that, there is a term that is effective nuclear charge. Let me introduce to a term that is effective nuclear charge. Effective nuclear charge is referred to as Z effective, and it is equivalent to Z minus screening constant minus sigma. Effective nuclear charge is Z effective, and Z over here is referred to as nuclear charge. It is referred to as nuclear charge, or you can say the attractive forces or the attraction that is being occurring. And the sigma basically represents the screening constant or the shielding constant. Now I will explain you what are these terms one by one. Now I will explain you these terms that are used over here. First of all, for this, consider that I have this as my nucleus. Okay, let us say if it is my nucleus, I have this as my first shell, second shell, third shell, fourth shell. Let us say this is my outermost shell, right? Over here we have certain electrons. Let us say one electron over here, two electrons. Then in the next shell, 1, 2, 3. Now in the next shell, 1, 2 electron, 3 electron, 4 electron, and in outermost shell we have 1 electron. Now understand this concept very clearly, very easily. It is very easy if you understand, if you see what is present over here. This electron which is present in the outermost shell is referred to as valence electron. This electron which is present in the outermost shell is referred to as valence electron, right? These electrons which are present inside are referred to as innermost electrons. These are referred to as which electrons? Innermost electrons. Now understand what will happen. Now it is very easy to understand. You just have to stay focused. See, this valence electron will face two kinds of forces. It will face two kinds of forces. Which forces? Attractive forces as well as the repulsive forces. It will face two kinds of forces, attraction as well as repulsion. Now understand this concept very clearly. If I talk about over here, see, this electron, nucleus is a positively charged species. So nucleus wants this electron to come towards itself. Why? Because electron is a negatively charged species, nucleus is a positively charged species. What happens basically? See, positive charge will attract a negative charge, right? Negative charge and negative charge will repel each other. Positive will repel each other, right? So what is happening over here? Nucleus is a positively charged species. It will attract this negatively charged valence electron, the outermost shell electron, towards itself, because positive attracts negative. Now this is what force, which kind of force? Attractive force. Now next thing. Really sorry. Now see over here. These innermost electrons, these all electrons are negatively charged. Just right now I have told you, a negatively charged species will repel a negatively charged species. They will not attract each other. What it will do? It will repel each other. They will repel. These all electrons will repel. Now when they will repel, what they will do? They will say the outermost shell electron, the valence shell electron, to not come inside, because we are doing repulsion. So the innermost shell electrons are responsible for causing repulsion to the valence electron, and the nucleus is attracting that valence electron towards itself. So it is showing attraction. So basically the valence electron can exhibit two kinds of forces, repulsive forces as well as attractive forces. Now the repulsive forces are referred to as screening effect or shielding effect. Okay. Now this repulsive forces is referred to as shielding effect or screening effect. Why? I'll tell you. See, basically what is happening? Nucleus is pulling the electron towards itself, while other electrons don't want the electron to go inside. Why? Because electron will repel each other. Negative will repel each other. They don't want the outermost valence shell to come inside. So what they will do? They will do repulsion. Now when they are doing repulsion, they are pushing the electrons towards outside. They are protecting the nucleus. They are not letting the electron to come inside. Now when they are protecting the nucleus, they are creating a shield. How they are creating a shield? By causing repulsion. So that is what is shielding effect. Shielding effect is being caused by the inner electrons, so that the valence electron could not come inside. Are you getting my point? Right, now coming back over here, this is your screening effect. This is your attractive forces that the nucleus is exhibiting. So basically when you measure it, okay, you'll get your effective nuclear charge. Now when I'll come back to this particular segment, in which of the following what will happen? Will the Z effective be more or the screening effect be more? This is the major responsible phenomena. Okay, one more thing I want you all to write it over here, that when I talk about Z effective, no students, Z effective is inversely proportional to size. More the size, less is the effective nuclear charge. More the size, less is the effective nuclear charge. Now just observe over here. Okay. See over here what is happening. When you are moving from scandium to manganese, over here at this process, Z effective students is more than screening effect. Z effective is more than screening effect. In which case, when you're moving from scandium towards manganese. Why? See, Z effective is basically referred to as the attractive force, we can say. Screening effect. Now, just forget Z effective. You know what is screening effect? It is repulsive forces. If repulsive forces is less, if innermost electrons are repelling less, that means now the outermost valence shell electron can come easily inside because now repulsion is less. When it can easily come inside towards nucleus, obviously the atomic radii will decrease. Now what is atomic radii? The distance between the nucleus and the outermost valence shell electron, right? No. So if there is less repulsion, that means it has a tendency to attract. Either it will do attraction or it will do repulsion. If repulsion is less, then obviously attraction is more. So electrons will come inside. Electrons coming inside, that means the distance decreases between the outermost valence shell electron and the atomic radii will automatically decrease because the distance between nucleus and the valence electron decreases. So atomic radii over here decreases. Now when we talk about Fe, iron, cobalt and nickel, they almost have same, equal. Why? Because over here, the Z effective and the screening effect are almost the same. The values are almost the same. So over here we can say the Z effective is almost the same as screening effect or the shielding constant. Now coming to the last, why atomic radii increases? Because over here it is quite simple. Now Z effective is less than the screening effect. Now what is screening effect again? Screening effect is repulsion. Now if repulsion is more, what will happen? If innermost electrons are repelling more, so it will move it away. The valence electron will move so away. Now valence electron, if moving away, atomic radii will increase because the distance between the nuclei and the valence electron automatically increases due to repulsion. Yes, so atomic radii will increase. So this is really very important, students. You have to put a huge star mark for this. Similar is for 4D series and for the 5D series, but 3D series are generally asked, so we have done it over here. I'm giving you a minute in order to write it down fast. Write it down fast, my dear students, so that we can move on to the group now. So that we can move on to the group part. This was for a period. This was for a period. Now, one more thing before going to the group portion. There is an order for screening power that you should know. The screening power of S is more than P, then D, and then F. This is the order for screening power. Okay? This is the order for screening power. This also you should know. Shall we proceed? Now this was for 3D series. I guess you all have written this. Take a screenshot. Now, moving on for the group. Order of atomic radii for group. Now basically in group we get 3D series, we get 4D series, we get 5D series and so on. So what happens over here? See, basically what is happening? If I write the elements over here, see, I have scandium, titanium, vanadium, okay? Then we move forward, okay? I'll write the last element, that is zinc over here, right? So if I write the below elements, we have yttrium, okay? Then we have zirconium, and I'll write the last one, that is cadmium. Over here, the last is cadmium. Over here, if you want to write it's lanthanum, it's hafnium, and just write the elements. See, what I want you all to understand over here, this basically which I have written is your group number 3rd. This basically which I have written is group number 4th. Here is group number 5 which I have not mentioned. Okay, then this is your group number 12th, right? So do remember, when we are talking in group, the trend basically changes. How the trend basically changes, I'll let you know. Okay, how the trend basically changes. See, basically when you move from top to bottom in a group, what happens in a group? If this is top and if it is bottom, you are moving from top to bottom. While moving from top to bottom, you know size will increase. Why will size increase? Now you have done the p block elements chapter as well. I've told you, when you move from top to bottom, number of shells increases. Now when number of shells increases, the distance from the center of the nucleus to the outermost valence shell also increases, right? So what will happen? If number of shells is increasing, the size also increases, right? Now this is order for general case. This order will be only valid for the case of group number third elements. So the order will come out for this. Now if you have to write the order for group number third for atomic radii, yes, the size will increase. Lanthanum will have more atomic radii than yttrium and scandium. But there is an exception now. Exception is for group number 4 to group number 12. What is the exception? 4D series have equal atomic radii as 5D series. This is the exception. 4D series will have equal atomic radii as compared to 5D series. That means yes, the trend should be like the atomic radii is being increasing, but 4D series have almost equal atomic radii to the 5D series. Now students, why is this happening? Why is this happening over here? Why does the size do not increase over here? What is the reason behind this? So the reason over here is lanthanoid contraction. The reason over here is lanthanoid contraction. Now what is lanthanoid contraction, ma'am? I want first of all so that you can write it down. Now I'll explain you what is lanthanoid contraction. I am giving you a minute. Kindly write it down so that I'll let you know what is lanthanoid contraction. Okay, now see over here students. Just right now I have told you, if I talk about screening power, S has more than P, than D and F. F subshells are the one, F subshells have least screening power. They have least screening power. That means they have least repulsion. Now understand this concept very easily. If they have least repulsion. Now why I am saying if, see, I am talking about F subshell. Forget that we are talking about this. F subshell, if I have least screening power, that means least repulsion. If repulsion is less, automatically attraction will be more. If repulsion is less, then the outermost electron will come towards the nucleus and the atomic radii will decrease. So the atomic radii decreases if repulsion is less. Now coming back to our part. What is happening over here? See. Just see the periodic table, you'll get the concept very clearly over here. If I look up to the periodic table, in group number third, there is no F block element. There is no entry of F subshell. But when you come across the 58th element, or you can say when you go in group number fourth, you see the atomic number over here is 72. From 72 to 80, there is an entry of F subshell which is completely filled. Because from 58th element till 71 element, we have F block elements. That means over here, the electron was entering into the F subshell. Last electron was entering into F subshell. Now what happens in the atomic number 72 element? Over here, from 72 onwards, F subshell is now completely filled and the electron is now entering into the D subshell. That's why they're D block elements. So in the case of lanthanum, there is no F subshell present, but from the 72 element, we have F subshell which is completely filled. Though last electron is entering into D subshell, but there is presence of F subshell. That means when there is F subshell present in this particular group, from group number 4th to group number 12, we have F block elements in their electronic configuration. F subshell has the least repulsion. If it has least screening power, least repulsion, atomic radii will decrease. Hence their atomic radii will decrease. For the case of 4D and the 5D series, it becomes equal. Their size will become equal. But why it is not happening in group number third? Because over here there is no presence of F subshell. So this is really very important. I want you all to write it down, students. Yes, so that we can move on to the next part. Kindly write it down so that we can move on. Really sorry. Kindly write it down. Now students, this was the very first property that we have to study in this particular topic. Now comes the next property with regard to d block elements. That comes out to be the metal lattice. Now the next property comes out to be metal lattice. See, if I talk about metal lattice, I have told you that transition elements or the d block elements, transitional elements are metals, so they will form metal lattice. Now they will form metal lattice, but who will not form metal lattice? See, I have written over here transition elements are forming metal lattice, but you know that pseudo transition elements, that is zinc, cadmium and mercury, that is group 12, they won't form any metal lattice. So there is an exception over here, exception, that is zinc, cadmium and mercury. You can even write it down, zinc, cadmium and mercury won't form crystal lattice or metal lattice. Only transitional elements, as they are metal, they shall form the metal lattice structure. Now students, what kind of structures are generally observed? This you need to know, but there is also one more exception which will not form any kind of metal lattice. There is one more exception, that is manganese, Mn. It will also not form metal lattice. It will also not form metal lattice. Now students, other than this, we have different groups. For example, if I talk about group number 3rd and 4th. Group number 3rd and 4th forms HCP structure, that is hexagonal closed packing. Is it clear? Now comes group number 5 and group number 6. They form BCC structure. Also, if I talk about group number 7 and group number 8, they will form your HCP structure. And if I talk about group number 9, group number 10, group number 11, they shall show you CCP structure. See, group number 12 won't show any kind of structure, that I have already mentioned. Also, there is an exception of iron. Fe will show BCC structure. So basically there are two exceptions and also the group number 12 as an exception, right? Kindly write this property so that we can move on to our next part. Right, now we are going to start with the melting and the boiling point. Now we are going to start with the next property, that is melting point. That is melting point and boiling point. See, basically students, melting point and boiling point will depend upon your electrons. Which electrons, ma'am? Valence electrons. More the number of valence electrons, more will be the bonding, and you will require more amount of heat in order to break that bond, so more will be the melting and boiling point. So what I'm writing over here, more the number of valence electrons, more is the bonding, and more will be the melting point and boiling point, and more will be the melting point and boiling point. So my question to you all is, which has highest melting point and boiling point? Which has highest melting point and or boiling point? So many of the students will say that, ma'am, the group number 5 can have, okay, as you can see over here, ma'am, they can have, sorry, not group number 5, group number 7. Many of the students will say, ma'am, group number 7 will have the highest melting and the boiling point, but it is not true, students. Group number 6 has the highest melting and boiling point. I'll tell you the reason why. You can mention it over here, that group number 6 elements, that is chromium, then we have molybdenum, and then we have tungsten. Chromium, molybdenum and tungsten, they have the highest melting and boiling point. What is the reason over here? Because they have 6 unpaired electrons over there, which are highest. If I talk about chromium, the configuration is 3d5 4s1. If I talk about molybdenum, the electronic configuration is 4d5 5s1. If I talk about tungsten, the configuration is 5d5 6s1. Right? So over here, these are the configurations for them. Right? Yes, ma'am. Over here, if you see 5 plus 1, how many unpaired electrons? 6 unpaired electrons. Again, 5 1 unpaired electron 6. Over here again unpaired electron is 6. How you can write it like this? See, F basically have 5 orbitals. D basically have 5 orbitals. D sub shell have 5 orbitals. F has 7 orbitals. So over here, if it has 5, how many electrons are filled? 5. Also in S, 1 electron is present. So they are unpaired electrons. Total how many unpaired electrons? 6 unpaired electrons. So more highest number of unpaired electrons are present in this particular group. Hence we can say that they have the highest melting point as well as the boiling point. Kindly write it down, my dear students. Kindly write it down. Yes, I hope so you all have written this. Now, one more question which they can generally ask you with regard to melting point and boiling point is, which has the lowest melting point and the boiling point? Which has the lowest melting point and the boiling point? My question to you is this. Now, lowest will be one which have the less number of valence electrons, right? Which have the less number of valence electrons are the one which will have the lowest melting point and the boiling point. Now, which are them? They are basically zinc, cadmium, mercury. Why? Because they have completely filled electronic configuration. It is already filled. If it is already filled, 3d10 4s2, 4d10 5s2, 5d10 6s2, they have completely filled. So they don't have any valence electrons. Hence, they have the lowest melting point and the boiling point. Other than this, students, as I've already told you while I was asking you the highest melting and the boiling point, I asked you that you might think that group number 7 are the one which have highest melting and boiling point, though they have less melting point and boiling point. Okay, so group number 7, this is also an exception that they have less melting point and boiling point. Is it clear? Now this was the order with regard to melting point and boiling point. Now kindly write it down so that we can move on to the next property of ours. Now the next property, students, comes out to be enthalpy of atomization. The next property comes out to be enthalpy of atomization. Enthalpy of atomization. Now, what do you refer to as enthalpy of atomization? First of all, understand what is atomization. As I've told you that the transition elements have a tendency to form the lattice structure. That means they can form this kind of structure because they have a tendency to form the crystal structure. So they can form the crystal structure in such a way. Am I right? Now, what happens over here is the amount of energy that you require to break these bonds so that they can be converted. First of all, for example, these are the lattice site. Now, let me tell you something. This is quite related to solid state. Basically, this is a lattice. Now, what is a lattice? Crystal lattice. Crystal lattice are the one in which elements are present in such a way, right? These are the lattice points. Lattice points are the points on which the atoms are being kept over, or ions or molecules are kept over. So, basically over here, this is the lattice point where atom, molecule or ion is kept over, right? So, the energy required to break the bond between the atoms or the ions. So, basically now we are talking about atomization. That means we are talking with respect to terms of atoms. So, the amount of energy required to break the bond between the atoms so that first of all it can be converted into which form? Solid form. This is the lattice site. Okay. Then further it can be converted into gaseous form. So the amount of energy that first of all you require to break it, to convert it into solid, and then to convert it into gaseous form is enthalpy of atomization. So this is the property that usually the D block elements exhibit. Great. Okay. Now we shall move on to the next property, that is the ionization enthalpy. I guess this you have written. Right, students. Now comes ionization enthalpies. Now if I talk about ionization enthalpy, again we have to write the period. That is the 3D series. Let us write, because 3D series is very important. What is 3D series? Again, school teacher vanishes. School teacher values chemistry mechanism which brings faith, confidence and comfort zone. Yes. So can we write all the elements over here? School teacher values chemistry mechanism which brings faith, confidence and comfort zone. Am I right? Now what happens usually when you move from left to right direction? When you go from left to right direction, my dear students, size decreases. This is the general trend I am saying. General trend, not with respect to this. Ionization energy will increase. Yes, ionization energy increases, but there is an exception. If ionization energy increases, this will be the order. This will be the order. But exception takes place at 2, 6th and 7th position. What is the exception? 2nd position, 6th and 7th position. Okay, kindly write it down first of all. Kindly write this down, my dear students. This is the order for ionization energy that they can generally ask you over here. Then they can ask you from over here. Kindly write it down. Okay. What is ionization energy? The amount of energy required to remove the electron from the outermost shell, right? Now see students, what is happening. If the order that they generally ask you, what is which has the first ionization energy value highest? Which will require more energy to remove one electron from the outermost shell? Just think about it. Which will require more energy? Obviously, which is completely filled will require more energy. Now, which is completely filled? Group number 12, ma'am. Zinc, cadmium, mercury. Yes, they will have the highest first ionization energy. Okay. Now, you have removed one electron from the outermost shell. You require a lot of energy in these elements because they were already completely filled. If I ask you second ionization energy, that means now again you are going to remove one more electron. That means total of 2 electrons now you have to remove, which will have the second ionization energy as highest. Which will have the second ionization energy as highest? What will be your answer? Ma'am, my answer will be that chromium and copper will have this. Why, ma'am? Because when in chromium, in the case of copper, if I talk about what is the configuration for copper, it is basically your 3D 10. Chromium, it is 3D 5. You know that in the case of this, it is 3D 10 4s2. You have to remove 2 electrons. 4s2 are gone. 3D 10 are still left. That means high amount of energy you require. Again, over here, see, it is what? It is your basically, again, there was an exception in the case of chromium. It was 3D 5. Sorry, really sorry. It is basically 3D10 4s1. One electron from the s subshell, 3D10. Again, you need more energy to remove from 3D10. So, high amount of energy is required. In the case of chromium, again exception. What it is? 3D5 4s1. One electron is taken from the s subshell. Now, 3D5. More amount of energy required because it is half filled configuration. Now comes when you have to remove one more electron. So this is your homework. You have to tell me the third ionization energy will be highest for which element. This you have to write in the comment section. So it will be interesting if you participate in what questions I give you. This is your homework. You have to tell which will have the highest value. Now moving on to the next property that comes out to be oxidation state. Now we will be doing the next property, that is oxidation state. Now all the elements in the D block elements show variable oxidation state except scandium and zinc. Okay, all the elements in D block elements in D block shows variable oxidation state except what? Except scandium and zinc. See, if I talk about scandium, it will show +3 oxidation state only, and if I talk about zinc, it will show only +2 oxidation state, but rest can show many. Now let us write the rest of the elements first of all over here. Rest elements are scandium, titanium, vanadium, chromium, manganese, iron, nickel, cobalt, sorry, iron, cobalt, nickel, copper, zinc. It is school teacher values chemistry mechanism which brings faith, confidence, and comfort zone, right? Now, what happens? See, I've told you scandium will show only +3, zinc will show only +2. If I talk about manganese, students, manganese will show +2, +3, +4, +5, +6, and +7. These oxidation states are exhibited by manganese. If I talk about chromium, it will show +2, +3, +4, +5, and +6. It won't show +7 oxidation state. If I talk about vanadium, it will show +2, +3, +4, and +5 oxidation state. Okay. If I talk about titanium, it will show +2, +3, and +4 oxidation state only. Is it clear to you? Kindly write it down. Now talking about iron, it can show +2, +3, +4. It will not show +5 but can show +6. There is an exception you can see over there. Okay, it can show +2, +3, +4. Similarly, nickel can show +2, +3, +4. But if I talk about copper, it can show +1 and +2 oxidation state. So these are the oxidation states that are generally exhibited by these blocks element. Is it clear to you, students? Right. Kindly write it down, students, so that we can move on to our next part over here. Kindly write it down. Now moving on to the next property of ours. We have M+2 M electrode potential. Now let me tell you this in brief. Basically what is happening, we are converting from M to M+2 stage. That means 2 electrons we are removing over here. Okay. That means whose value of electrode potential will be high? More negative potential, more easily the cation is formed. More negative the electrode potential, more easily cation is being formed. Okay, so which will have highest negative electrode potential? Which will have the highest negative electrode potential? Which will have the highest negative electrode potential value. This is really important. And now over here, it is manganese, nickel, and zinc. They will have the highest one. Why? First of all, if I talk about the zinc, basically zinc has 3d10 electronic configuration. It is 3d10 4s2. When you remove 2 electrons, it is 3d10, which is completely filled configuration. When I talk about Mn, it will be 3d6 again. Okay? What will happen in the case of nickel? Now students, when I am talking about in the case of nickel there is high hydration enthalpy. That's why they have the highest negative electrode potential. See, highest negative electrode potential values are the ones which are completely stable. The one which becomes unstable after losing 2 electrons will have positive electrode potential. For example, if I talk about Cu, it converts into Cu+2. When Cu converts into Cu+2, it is moving from which oxidation state? From 3d10 it is moving to 3d9. Then that means what is happening over here? It is becoming unstable. This is unstable. Now when it is becoming unstable at 3d9, because 3d10 was stable, so it will have a positive electrode potential value, not a negative one. Negative potential value will occur when it will become stable. But when it will become unstable, it will have a positive value. Is it clear to you? Now, these are the very little things that you should know in this particular topic. Right, students? Now, further properties we shall discuss in the next lecture. For today's lecture, this much is sufficient. I want you all to practice the questions that are being provided to you in your practice sheet. So, your homework for today is solve question given in your DPP. Also, the next lecture is going to be a big lecture because we are going to complete the properties with respect to this. After that, we are going to see the compounds and then we'll move forward to the F block elements. So, do solve the questions in the DPP that are being provided to you. Yes, if you have any doubt, you can write in the comment section. Also, read the NCERT of the topic that I have been given you. Now, I am ending this session today because here atomic radii, ionization enthalpy, these are really very important. I want you all to understand each and every concept in very detail. Right? So, thank you so much, students. Now, we shall meet in the next lecture. Till then, keep smiling, keep learning. Bye-bye.